Good afternoon, everybody, and welcome to today's Cutter Transportation webcast. Before we get started, I'd like to give you a little bit of a brief introduction to our presenter today, Mr. Sean Barbeau. Sean is a principal mobile software architect for R&D at the Center for Urban Transportation Research at the University of South Florida. His research interests include multimodal mobile applications, open source software, standardized open data, and cybersecurity for mobile phones and transportation infrastructure. Okay, Sean,
Um,
take it
Today,
away.
thank you very much. Today I'll be talking about a project that we recently completed called Improving the Quality and Cost Effectiveness of Multimodal Travel Behavior Data Collection. To give a general introduction here, multimodal transportation is vital to supporting livable communities. So you can think about basically any way that people get around other than driving alone here. So some examples include public transportation, biking, walking, ride sourcing. Things like Uber and Lyft, car share, bike share, scooter share, you name it, basically, and any other way that you can get around. But one of the challenge here is that current data collection techniques to understand multimodal travel behavior have significant limitations. Looking at this from the public transportation side of things first, transit agencies will typically do onboard surveys to understand where transit riders are riding to and from. But this will, of course, miss anyone who's not on the bus or not boarding the bus, depending on when the onboard survey is being done. So you're missing any riders that may have chosen not to ride the bus on that particular day for a reason. And these are done typically. They require a lot of effort. They're not done frequently. Activity diaries and surveys are another way to collect travel behavior information. So these could include handing out, pen and paper or electronic diary to someone who then records where they travel to and from, and the different activities that they do throughout the day. But these, again, are time limited to a few days because of the effort involved, both the participant side of things and then manually post processing all of the collected surveys. So in the past, there's been multiple different types of mobile apps that have been built to be an electronic version that installs on someone's phone that would potentially replace a paper activity diary. But some of the challenges with these are difficult user acquisition. So these users, again, really don't have any incentive unless you pay them or offer some type of incentive for them to install the app on their phone and then constantly input information. If you're trying to do even just a passive version of an activity diary, so trying to have an app that runs in the background that records location data over time, in the past, these have had significant negative impacts on battery life. It costs a lot of energy to use things like GPS very frequently to record breadcrumb trails of exactly where someone is going. And then if you try to get around that and say, okay, well, we're not going to track the user all the time. We're going to just have them tell us when they start and stop a trip by tapping a button in an app. It can be hard for users to remember to do that manually, starting and stopping. It's just another, one more thing a user has to remember throughout the day. So all of these issues collectively really prevent a better understanding of some of the real world challenges that we face, whether it's understanding why people are picking different modes of transportation, whether they're taking transit instead of an Uber or Uber instead of transit, and also relationships between travel behavior and health. What types of activities are people doing throughout the day, and how does that impact their health? So this project, as I mentioned, it was funded by the National Center for Transit Research, improving the quality and cost effectiveness of multimodal travel behavior data collection. So this ran from early 2018 to early this year, 2020. We just recently wrapped up the final report, which is available at this link if you would like to download and read about all of this in detail. So our goals for this project were to try to address some of those challenges that I mentioned earlier. So specifically, how can we capture activity data, and specifically when someone is starting and ending an activity and where they have started and ended that activity? How can we do that on a mobile device, how can we transfer this data from the mobile device to a server where it can be processed by transportation professionals, and how can we do that while avoiding negative impacts on the user, and in particular, battery life was at the top of our list. That's one of the, as I mentioned, one of the biggest challenges for doing passive travel behavior data collection. And then also, how can we deal with this issue of the problem of acquiring and retaining users? Avoiding the problem of making someone go and download a special app just for the purpose of tracking where they're going. So looking specifically at the challenge of recruiting and retaining subjects. So these are some of the apps that I was referring to earlier that were developed specifically for replacing travel behavior surveys. So there was a Track It project, which was a project that several of us at Cutter worked on. There's been other projects, Future Mobility Survey, Quantified Traveler, Smart Track, Florida Trip Tracker. But all of these apps suffer from the same user fatigue issue of either manual recording trips if the user has to start and stop their trips by tapping on a button in the app. And they've really only been deployed in very limited, small settings, either for a very small time duration or a very small group of users. And there's really no ongoing incentive, as I mentioned, unless you pay the user and provide them some type of financial or otherwise incentive for the user to install the app, keep it installed on their phone, and then perform any activity they need to, whether it's tapping on the button to start and stop the trips to contribute their travel behavior. And again, these many of these apps, including the ones that we developed, really battery life and the negative impact on battery life was one of the key problems that we saw with that app. So a solution that we found here is looking to see what was already out there in the industry that we could potentially leverage. And one project that we've been involved with at USF is called OneBusAway. And OneBusAway is an open source software platform for real-time information. It's been deployed in several different cities around the world, including here in Tampa, also Seattle, San Diego, Washington, D.C. And it's supported by a 501c3 nonprofit called the Open Transit Software Foundation. So this is a group of transit agencies, universities, consultants, and independent developers. And this project started at the University of Washington as a grad student project to really just help transit riders and provide them real-time transit information in a format on mobile devices that was easy to access. So the agencies have an incentive to deploy this software because they want to provide services to their riders to let them know when their bus is arriving. There's been several research projects done, including several that we've been a part of, that have shown the benefits of telling the transit rider when the bus is going to arrive in terms of less actual wait time, less perceived wait time, and just overall satisfaction with the transit agency. So the agencies see an advantage in deploying and leveraging an open source project that multiple transit agencies are working on, as opposed to just implementing their own app, for example, which could be cost prohibitive in many cases. There's a large number of users of the OneBusAway platform, and looking just at the iOS and Android apps, there's well over 1 million unique users, and typically on the order of about 330,000 active users looking over the last 30 days. There are hundreds of thousands of more users when you look at users of the websites that are deployed in various white label deployments. A few deployments, such as in Argentina and New York region in Canada, where the transit agency has taken the OneBusAway software and then just put their, changed the color and put their name on it and deployed it in their city. And then two, the reason why the University of Washington was originally involved with this is it's a platform for research, for understanding how users use the technology, how the technology impacts the users. And so this was something that we looked at to potentially be able to leverage the existing OneBusAway open source apps that are deployed to a large number of users, and then add the ability for users to opt in if they would like to contribute travel behavior. And believe it or not, we've actually had some users prior to us starting this project say, we'd really like to be able to contribute data. This is, we see this as something, trying to help out the public and public sector transit agencies and users, as we'll see, are surprisingly willing to opt in to contribute this type of data. So some of the Open Transit Software Foundation members, University of Washington, USF, Georgia Tech, New York MTA, WMATA in Washington, D.C., HART here in Tampa, York Region Transit, San Diego MTS, Sound Transit in Seattle, Cambridge Systematics, Go Europa, Transit Screen, and Trillium are just a few. And you can go to the website if you want to get the full list. So moving on to looking at the second challenge that we were trying to address here. So when we're trying to detect activities, like I mentioned before, the GPS, which you would typically use for location of locating the device if the user is traveling outdoors, every time that you want to sample the user's location with GPS, that costs a lot of energy. And so here's a graph here that shows this kind of period of the user. Every time that we want to sample the GPS, the main application processor has to turn on, which causes a spike in energy cost here. And then you have the actually acquiring the user's location using GPS hardware, which also costs energy. And then it'll drop back down until the next time you want to sample the user's location again, and then it'll spike back up. So this constant pulling of GPS data, which can be as often as every 4 seconds or 15 seconds, if you want to get a high resolution view of their path, really eats up the user's battery very quickly. So there's been some advancements in mobile phone hardware, and a lot of this has been driven by the concepts of trying to understand. Have apps that can monitor the user's health and activity and steps throughout the day, that type of thing. So that's driven this design where instead of having to power up the main CPU to do these periodic tracking, we now have something called coprocessors, sensor coprocessors. So these are kind of, you can view them as like a miniature version of the CPU that's designed to do a few things, a few special things very efficiently. And so a lot of the logic related to tracking activities, to monitoring sensors like accelerometers and gyroscopes inside the phone, this has all been delegated to the sensor coprocessor now, which takes a fraction of the energy of the main CPU to run in the background. And the Android Activity Transition Application Programming Interface, or API, launched in March 2018. So this API then allowed mobile apps to listen to these sensor coprocessors to be notified when there is some type of activity transition happening. So this allows you, an app then, to, instead of having to just periodically wake up the main CPU, it can just wait for a signal from the sensor coprocessor, which consumes much less energy. So, and these sensor coprocessors are active constantly in the background, even when your phone the screen of your phone isn't on, when it's just in your pocket. So this now, again, looking at the same graph that we saw before on the left, with the main CPU having to power up and spike up every time you wanted to track the user's location to figure out if they'd moved or not. Now we have a design on the right that shows the sensor coprocessor here in green, which is kind of this constant low-level energy cost. But it does the monitoring of the sensors for you. And then when it detects a transition in an activity, it notifies your app and the main CPU. Then you get the one spike to say, okay, now I want to capture the user's location or do something else now that the user's actually moved. But it avoids these constant spikes very frequently in energy cost. So for our research project, we took advantage of both OneBusAway and the new Android Activity Transition API, and we added software to the OneBusAway app that listened for these activity transitions. And as of when we were doing this project, so in 2019, there were the activities that were recognized by the underlying hardware are something called in-vehicle. So it's an in-vehicle activity, on bicycle, running, still, and walking. So we would get an update, and our software would start running, our app would start running when a user transitioned between any of these different activities, including from still to running or still to in-vehicle. So as you notice, in-vehicle is not split out into what type of vehicle are you in. Is it a personal vehicle or public transportation? And that's something that I'll talk about a little later. So each time we get one of these activity transition API updates to when the device tells us, okay, the user has transitioned from one activity to another, we also get a confidence value from 0 to 100, and that's is supposed to give us some indication of how confident we can be in the fact that the user's actually made the transition that's been detected. And that's defined by the Android as the likelihood the user is performing this activity. And then after each transition trigger, when we get the notification the user's activity has changed, we also then our app fires up and captures location data from the 3 different location providers that are available on Android devices. And these different providers include global navigation satellite systems, GNSS, and so GPS is one example, the US GNSS. And these are satellite-based positioning systems that use satellite signals from outer space to figure out exactly where you're located. Also network-based providers. So this is using information from your cellular network or your Wi-Fi network that you're nearby or connected to indicate where you're located. And then the last one is a fused location provider. So this is kind of a smarter implementation from Google that tries to take a number of different sensors, GNSS and network information, fuse it all together, and give you some type of location. So all 3 of these providers can have different levels of accuracy as well as different latencies for how long it takes to actually acquire a position. So we made the decision to just capture data from all 3 and then store that and then figure out later which was the quote like best one to use for any given activity transition. Within the app, we also collect data that when the user goes in, so assuming the user's opted in to have their data, for us to be able to collect their data, we also monitor which screens they're looking at. And in particular, when the user looks at a list of arrivals, we capture what arrivals they're seeing in the app and then the delay, which could potentially be used to understand why the user maybe didn't take a Route 5 on this particular day if the Route 5 was running 15 minutes late, something like that. We also capture the trip plans that the user makes within the app, so both the origin and destination they put in, as well as the options that they get back showing the different, whether it's a combination of, for example, the shown here, bike share in transit or just bike share, and so we understand what options we showed to the user. And we also capture whenever the user sets a destination reminder. So there's a feature that will alert the user when they should get off the bus based on their personal stop for their trip. And so we capture that as an indication that to tell us if the user sets that reminder, it's a pretty good indication that they're actually on that particular transit vehicle. And that could then be used later to help us determine whether in vehicle transition was actually them getting on the bus versus getting in a personal vehicle, among other things. So this diagram here just shows the execution from kind of beginning to end of our different data collection activities. And as you can see, some of these happen in parallel. So this is actually relatively tricky from an implementation perspective to make sure that all of this happens correctly and at the right times when you can have things happening in parallel. So looking at starting at the left-hand side, so the app initially registers. So if the user opts in for us to collect their data, the app registers for activity transitions when the app first starts up. And then it basically just waits. The user could put the app in the background and go do other things. And then eventually when the sensors on the device trigger a activity transition. The sensor coprocessor triggers that. Our app will receive an update that says, okay, the user started walking, and then we kind of branch off to do a couple different things. We read so looking at the top branch, we read any cache data from when the user used the app. To say, okay, now we need to save if the user just looked at arrival times in the app or did a trip plan or set a destination reminder. We save all that information along with that activity transition. and also calculate some of the times of when these events are actually happening, as well as requesting location updates from the different location providers, and then getting the activity recognition confidence value so we know a rough indication of what the device thought, how confident the device thought it was in terms of estimating a particular transition. So that covers the data collection piece of the different pieces of data that we are collecting in this particular project. So looking at how we're storing the data, so we made the decision to use Google's Firebase Cloud Storage, Cloud Firestore, for storing the activity transitions, the locations that we calculate when the user makes a transition, as well as some of the app usage information of what arrival times they see, etc. So this is a NoSQL document-based storage, so it's a little bit different from your traditional SQL-based uh, database. And the advantage of the NoSQL document-based storage is you can kind of just save chunks of data. This scales very well. We can support a huge number of users in collecting this type of information. And we still have access to everything we need to be able to pull out data for a particular user to look at their information. So another advantage of using Firebase here is that the Firebase automatically syncs between when you save information on the device to a Google's servers. So we don't have to worry about actually doing this manual synchronization ourselves. And that really helps, again, looking at battery life and making sure that this is done very efficiently so that we aren't constantly pushing data into the background, in the background, which again can cost the user a lot of battery life. So each user is assigned a random universally unique identifier, which you see a list of just UUIDs, which were generated here in the middle column of the screenshot. So these are random IDs that can't be tied directly to the user. We also have a diagram here showing the user interface of enrolling the user in the study. So when the user opens the app so we rolled out the update to OneBusAway users, and they then, after they started the app a couple times, they saw a little pop-up that asked them if they'd like to improve public transportation. And then we ask if they're over the age of 18, and this was all reviewed by the USF-IRB to make sure, the Institutional Review Board, to make sure that we're protecting user privacy. And then we show them an informed consent document if they agree to enroll. And then at this point, we also capture their email address, and this is so that we could follow up with them with additional surveys via mail to capture things like demographics information, et cetera, which it's a little easier to answer some of those questions via an email than to implement and capture all this data in the app. So the other thing, which I will show here as well in the next slide. So for user privacy protection, we're actually splitting out the storage of their email addresses and the UUIDs, that mapping to one data store, and then all the activity transition data gets stored to a completely separate data store that has only the UUIDs and not the user email addresses. So this enables us to have someone looking at the activity transition data without directly seeing the emails if we want to partition off who has access to see that information. So something else that we had to go through here, so we're actually processing the data. The data that we get off the transition API is essentially a series of updates. So each of these blue nodes here is saying, okay, the user transitioned from X activity to Y activity. So they went from still to walking, and then later they went from, at this particular time, they went from walking to in vehicle, and then later they went from vehicle to walk. And then we have to take that representation and turn it into kind of your more traditional trip origin destination data representation. So in this representation, in a single record, you have the user started at one location and ended at the second location B, let's say A to B here, and they walked between location A to B. And then the next record is the location is that the user drove from location B to location C. In the next record, they walked from C to D. So going between those two different data representations takes it's a little tricky, and you have to deal with things like potential data dropouts. So if the user's battery died, for example, and you got an update before the user battery died that said they started walking, but then their battery died, and then looking at and then they plugged in their device, started it back up, you may never get a transition that says they stopped walking. So we need to do some kind of some data cleaning and tolerance for potential bad data blips here and there. And so we have, I'm not going to go into it in detail here just for time, but we have outlined in the final report how exactly we did this. Looking then at the data visualization part. So once we've captured the data and then transformed it into this more traditional trip origin destination format, we export it in a tabular format. So that's to a CSV file, which lets you open it, the data in something like Microsoft Excel, which you see a screenshot of here. And so this is kind of your traditional record where you see, okay, user started at one location, stopped at another location, and you have a start time, stop time, you have an activity associated with that, the confidence value, and a variety of other metadata. We also export the data to a spatial data format called KML, or the Keyhole Markup Language. And KML is a standard that is used in many different geographic information system products, including Google Earth. So that allows us to open the data in Google Earth. And so what we see here is a screenshot of a particular trip or trip link here from showing where the user in this particular situation is actually me, and showing a transition from when the user parked their car in the parking lot and then walked to the building and then sat down at their desk and started working. So what we would see in the data, we would not see in the data the blue triangle and blue circle. Those are just additional pieces of information I added to the screenshot here just to give you an idea of what the true start and end was at this particular trip. But what you would see in the data is the green triangle showing where this activity transition, the first activity transition happened to start this trip, and then where the red circle, where there was another activity transition from walking to still that says, okay, the user stopped this particular trip. And there's a few different interesting things that you can look at here. So the first is, if I enlarge the data here at the start location. So you can see, as you would probably guess, that the location provider that was used, that was selected. So we captured 3 different locations here from the GPS network and Fuse location provider. We have an algorithm, a very simple one that picks the quote best location. And I'll talk about that a little bit later. So we chose GPS as the best location here, which makes sense. We were outdoors, that's typically the case. And so you can see that between when I actually stopped my car and got out and started walking, there's a short lag here before we got a GPS fix back. And so it's the distance here is basically how far I walked. And we also have field a couple records higher here that shows the activity location time difference. So it's 0.2 minutes. So basically, it took me 0.2 minutes to stop my car, grab my stuff, and then walk towards the building, and then the green triangle is the location we got from GPS at that point. And the horizontal accuracy, which is a measure of how good the location is, was about 9 meters for GPS, which is pretty good for having the phone in my pocket and being in motion here. So then on the ending of this particular trip, you can see that the location provider, the second red arrow, is pointed at to show that this used the network location provider. So this was most likely based on Wi-Fi and knowing the position of Wi-Fi, this Wi-Fi access point. So you can see the location is actually really close, that it calculated to my actual desk location, which is the blue circle. And you can also see, though, there was a greater delay. If you look at the time difference, was 2.5 minutes. But I was stationary during that delay, so it really, in terms of looking at spatially and the difference between the actual where I actually ended the activity and where the location we captured is really not that different here. And this is kind of from what we've seen of looking and manually inspecting some of our own trips during this project. This is pretty much indicative of most of the data that you see, where there's a small delay here at the beginning to then capture the location at the start of the trip after you get the activity transition, and then at the end of the trip tends to be closer to the tree location. And these are the arrows then pointing to that time difference, showing the shorter time difference there where we started the trip between the blue triangle and the green triangle. So we deployed this software to collect data to the OneBusAway users in July of 2019. And there's an existing beta testing group of 676 users at the time. And this is a group of users that have just opted in at some point over the years. OneBusAway has been deployed for about 8 years now in different cities. It's been different amounts of time. But over time, users have volunteered and just opted in to get early software updates that maybe new features, maybe bug fixes. And so this was the group of users that we deployed the data collection software to. And as part of this project, we didn't provide any incentives to users. They just got the prompt that you saw earlier at some point when they opened the app after the update. It's just asked them, do you want to improve public transportation? And then they went through the enrollment process. And so as of September 19th of 2019, which is about 10 weeks, at that point, we had about 74 users enrolled in the study. And at that point, no users had withdrawn from the study, and no users had reported any reduced battery life or any other negative consequences. And over this 10-week time period, we collected about 1.7 gigabytes of data of both activity transitions and user app usage that happened just prior to an activity transition. So the following analysis I'm going to go through looks at this about 10 weeks of data collection. So we, in the initial export, looking at all activity transitions, which include transitions to still activities, which is the raw data that we get, there are about 113, almost 114,000 activity records. And just on the right is a rough share showing the different regions of where data was collected. Most of the OneBusAway users are located in the greater Seattle region where the app started. And you can see that region also contributed the largest number of activity transitions, and then followed by San Diego, and then Tampa, and then some of the other regions are smaller. And this roughly mirrors the user base of the overall OneBusAway application as well. So looking at trips by detected activity type. So if we remove like the still activities and then just look at, okay, if a user traveled for, made a movement and what type of activity was associated with that movement. And in the initial export that we looked at, you can tell that there's a huge number, like over 3/4 of the trips were walking, and next followed by in-vehicle. And so the reason behind this, as we found from when we were testing the application, is that it's very sensitive to the point where if you stand up and walk around the building and then walk back and sit back down at your desk, like it will actually capture those activity transitions of you standing up and then and walking and then you sitting back down. So what we did to kind of give us a better picture of what we would traditionally call trips of, looking at something more like home to work or kind of at a more macro scale, we filtered the data to filter out any trips that were short, that were less than 5 minutes in time, and anything where the travel distance between the origin and destination was less than 50 meters. So we filtered out the trips that were short in time and duration, and that gave us the share of trips on the right-hand side. And you can see percentage of in vehicle trips goes way up because we're filtering out a lot of the very short walking trips that are just, for example, walks around the building or walks around your home in the middle of the day. We also other studies may want to use different filters. So, for example, if you're looking at things like health and user activity, how much time is the user spending, up and around and moving and walking versus sitting still, then you may want to use a different type of filter here. And we've also found that there is sensitivity to where sometimes when the activity transition detects walking, it's doing that in real time and it's not always right. So sometimes you will get false positives to say the user started walking, and then it'll figure out, well, no, they didn't really start walking. They were just like, moving around at their desk or something like that without actually standing up. And then you'll get another transition and said, okay, they're back to still. We get some noise, which we'll see a little bit more about that in a second. But the bias towards being a little more noisy is a good thing. We can always post-process the data to remove that noise. But if you bias the other way towards, having false negatives where you would actually be missing trips, it's not as easy to recreate those trips that we're missing. So overall, given the type of data that we were seeing, we were relatively happy with the ability to capture trips when we wanted to. So looking here at activity confidence values, so there's a more extensive discussion of this in the final report. I'm just going to talk about this briefly. So looking at again, all activity transitions, the confidence values that we were provided by the device weren't as high as we had hoped they would be. But we think part of this, again, is due to the real-time classification happening and some of the errors when it says, okay, it thinks it's walking. Well, no, just kidding, it's not. So when we filtered the data, again, to look at just longer trips to try to eliminate some of these small false positives, we saw a much higher confidence values associated with the longer trips, where it seems the devices had a longer amount of time to be more confident in the activity that it's classifying. That being said, this is definitely an area where there needs to be more analysis and benchmarking to understand. We're being given this confidence value by the device, but we need to really analyze that, and so we have a better idea of if that confidence value itself is actually accurate. Something else to consider here is as I mentioned before, the time delay between when the activity transition is detected, which is usually based on sensors like accelerometers or gyroscopes, and then we get an event that says activity detected, and then we acquire a location. We ask the device for a location, and we'll get a location back. And there can be this time delay between when we are notified of the transition and when we actually get the location. So we looked at this potential delay between the activity transition and the location acquisition. We were overall relatively happy with what we saw here. So the 90th percentile of delay at the origin location, so where a trip starts, was just a little over 3 minutes, and the 68th percentile was about 14 seconds. So over 2/3 of the trips, there's a delay of less than 14 seconds between when the transition happens and we get a location. And the delays tend to be less at the destinations, actually, and looking at overall all the trips. And we believe that's because at some point during the trip, the device may have been active. And so the users or the device is in more of an awake state to immediately grab a location, as opposed to the user sitting still for an hour or two, and all of a sudden the device has to wake up and figure out what's going on. And so overall, we feel this is an acceptable trade-off for being able to monitor activities throughout basically 24/7 without a significant negative impact on battery life. Because the small delays that we do see seems to be a reasonable trade-off. So looking at the share of location providers, there was, interestingly, roughly even split between the different location providers. And this is something we could certainly look at more to try to understand better. We did see about 14% of the time we tried to acquire in a location, there was no location data associated with the activity transition. And so in these cases, we believe they're likely due to the fact that the user may have turned off location services on the device or may have denied the application access to location data for privacy reasons. It's not uncommon, especially these days, for users to turn off location to both save battery life and protect their privacy if they don't want their location to be known. And this is something we didn't force location. We didn't force users to leave location on if they didn't want to, although that's something a particular study could certainly do if they chose to do that. So we also looked at the estimated horizontal accuracy for all locations. So this is a metric that every time we capture the location, we again get a number from the device that says it's the radius of 68% confidence is the definition here. So that means that the radius that we get, which is the solid black line, 2/3 of the time, roughly 2/3 of the time, 68% of the time, the true user's true location will be inside that radius. The other 32% of the time, the user's true location will be outside of that radius. So this is kind of it's a confidence measure based on a number of different things that the device can measure. So some of the caveats to think about here is that we noticed in one particular circumstance on an older device, a Samsung Galaxy S6, or across all Android devices, there's something called battery saver mode. And this is something the user can enable if they want to save their battery, reduce the impact of all device functionality on their battery over a period of time. So if the user is getting towards the end of the day where their battery may be starting to run out, user may flip on the battery saver mode to make their battery life last a little bit longer than it normally would. And typically the device will slow down the CPU, it will make the screen dimmer, turn off background location processes, and do other things to try to reduce the impact on the battery. So we did notice on one older device, a Samsung Galaxy S6, that when battery saver mode was turned on, we didn't get any updates from the activity transition API. And we don't yet know how widespread this is. If this is across just older devices that don't have that sensor coprocessor, or if this could potentially impact newer devices as well. So this is something that we also need to look at a little bit more in depth. We did, after we noticed that this was happening, we did add the ability in the data collection software where now we do capture the setting that the user has on the device as to whether or not they've enabled this battery saver mode. So if all of a sudden we see that we're not getting data from a particular user, we can look at the setting and say, okay, this user has power savings mode turned on. That's why we're not getting any information. So this is something that can certainly be studied in more detail. So some of the enhancements that we made following that the initial deployment, that 10-week pilot deployment. So we added more analytics to capture if the user was leaving the study via the app settings. We actually rolled that out earlier on in that time window. Also in the enrollment process, we added analytics at each step in the process so we could see if users were dropping out, if it's 3 clicks to get all the way through. And so figuring out whether for the people that weren't enrolling, were they only clicking partially through and then stopping, or were they just, from the beginning, just not choosing not to participate? We also added a not now option when the user gets the initial pop-up where if someone's just trying to get into the app quickly to see when their bus is arriving. Initially, it was a hard, like you had to say yes or no, you wanted to participate. There was no option to say, maybe later. And so we added an option to say maybe later. So if someone was rushing to get their bus, they didn't need to worry about reading the full informed consent. They could do that later if they wanted to opt in later. And then we also added email confirmation to avoid typos in emails where the user has to type it twice before they click enroll. And then capturing the power saving settings, battery saver, like I mentioned. So future work here is definitely looking at classifying different types of in-vehicle trips. So as I mentioned before, we just get a notification that the user has transitioned to in-vehicle, but figuring out whether that in-vehicle trip was transit, ride sourcing, personal vehicle, et cetera, as something that we want to look at in detail. And there's been past research on mode classification, that type of thing, although most of the time it's taken place when you have a more high resolution breadcrumb trail of the path of the user and precise speeds, but not with just origin, destination, location information. So that's where this will differ a little bit from past research. Also looking at ground truthing of the accuracy and precision of the activity transitions, location, and mode data, as I mentioned before, is something that still needs to be done. Assessing when users drop off during enrollment, if we can streamline the enrollment process to get more users on board. Improving this best location algorithm that we have for picking the best of the 3 locations. Post-processing the activity mode data, filtering out what we need to for these, very short walking trips is another area. Also assessing the impact of the power saving modes, including demographics. Does this primarily affect users with low cost older devices where we need to be sensitive in studies to make sure that we're not potentially excluding these users? And then also looking at an iOS implementation. Our implementation here was just for Android. So overall, our conclusions were we were actually pretty happy with overall the data that we are seeing from these activity transitions using the new sensor coprocessors and just running in the background in a very energy efficient way. It's definitely a promising new tool for collecting origin destination data. From the preliminary data that we've examined, it seems like we get timely and accurate activity transitions and locations. No users reported any battery life issues, which is definitely a good thing compared to past studies and including the past app that we worked on in older projects. The ability to collect data from many users for longitudinal studies at scale. These are users that have OneBusAway installed on their phone and are going to leave it installed on their phone for a long time because they find a lot of value in it from a day-to-day basis. And as we saw from this particular study, we had a lot of users, basically 1/7 of the users enrolled without any incentives, just because they wanted to contribute their data. So there is a reduced data density when you look at traditional GPS tracking of getting this very high resolution every 4 seconds or so breadcrumb trail. But if you're mainly concerned with where users are moving to and from and how they're getting there, more the origin destination scale, this seems to be an acceptable trade-off. The software that we developed into this project is all open source. I have 2 links here to GitHub if you want to check out the OneBusAway app, which is the top link, and then also the software that we use to export the data from Firebase to the KML and CSV formats, the second link there. So in just a quick update, as we were wrapping up this project, we did one more snapshot, just looking at to see how many users were still enrolled. So user enrollment had actually gone up to 105 users out of the beta testing group of 740 users. So about 14% of the beta testing user group had enrolled in this pilot without any incentives. The hosting cost to store the 105 users' data in Firebase was about $7 per month using this particular plan that we were on. That can definitely differ depending on how much data you're collecting, which is a function of how often users are transitioning activities. So that may scale depending on your user demographics. And we plan to roll out the software update to all OneBusAway users shortly. And if anyone wants to enroll in the OneBusAway Android group and you happen to be in one of the regions and enroll, I have a link there to the beta testing group. Once again, this was funded by the National Center for Transit Research, and I also want to give a shout out to Charg Seaton, Dr. Charg Seaton, who was a great help in this project in implementing a lot of the software for doing the data collection and processing. So with that, if we still have time for questions here, I'm happy to answer any questions.
Hey, Sean, thank you so much for the very informative presentation. I will just remind everybody on how to ask a question. The Q&A box is located on the bottom right-hand side. Simply type in your question and or comment. And then Sean, it looks like we do already have a couple of questions. Before I get to them, I wanted just to remind everybody that a copy of today's presentation is available in the handout section, and a copy of the report is also available in the links section. Okay, Sean, the first question that comes in, it says, does where you carry your phone affect the accuracy of the data?
Yeah, that's a good question. So we there's two different parts to that. One is the sensor data. So depending on where you carry your phone, so for example, if you're carrying your phone in your pocket and your leg is swinging back and forth, that is a very clear indication that you're walking. The profile of the sensor data will look a little bit different if you're carrying your phone in a bag. And the bag is more like bouncing up and down rather than swinging like a pendulum. So I don't. It's not. We haven't done an analysis of that piece of it. I think that's something that we can definitely study more. Also, there would definitely be an impact on things like GPS, depending on where you have the phone located. We did do a study about 10 years ago looking at older flip phones and the position of where the phone was located, and it definitely did have an impact on the quality of the GPS fix we were able to get. It's something I think that could be studied more given modern mobile devices.
Okay, the next question is a two-part question. It says, is the data collected only when the user is using the OneBusAway app? And do you need the OneBusAway in your region or their region to use that mode for the tracking feature?
Yeah. So the after you install the app on your phone, the and you enroll in the study and you put the app in the background, it will even if you're not actively using the app or the app, even when the app is not active, it will capture the mode transitions, the activity transitions. Um, the and No, if for example, I guess if we wanted to use it in a region that did not have OneBusAway deployed, you could still download the OneBusAway app, and we would capture the data even if you're not actively using the app. The one caveat is that because we don't control when the data syncs from the device to the server, we know it syncs for sure when the user opens the app. So users that are frequently using the OneBusAway app, we would see their data pushed to the server pretty regularly. But depending on how often Firebase updates the data and how frequently someone wants to look at the data results, we may need to poke users to just open the app or something if they're not frequently using it.
And then the next question comes in and it says, is this feature currently available in all cities with OneBusAway?
So yes, anywhere where OneBusAway is available, this feature is available for users to opt in.
Okay, and then we'll take two more questions before we run out of time. Do other real-time bus location apps have similar feature for measuring trips by mode?
That's also a good question. So the short answer is we don't really know. We know that all apps collect some level of analytics data on their users. Um, the How the detail of which is not, I think, always clear. We do know that other apps will collect usage information while you're using the app, but may not do it while the app is in the background. Again, just for generally to avoid any impact on the user, potentially on battery life. So I'm not aware of any that are doing that, but it's not clear, and it's not something that I think apps typically advertise.
Okay, and then the final question says, what is the typical accuracy of the network location provider?
So the network location provider is based either on either the cellular network or the Wi-Fi network. So depending on where you're located, it can be very accurate. For example, like we saw when I was inside the Cutter building on the USF campus, We have a number of different Wi-Fi access points, and I think one's actually relatively close to my office there. So the position where it knows where the Wi-Fi router is, and the location was pretty close to my actual office location. If you're, however, traveling in a rural area where there's no Wi-Fi nearby and you're just connected to the cell network, and there aren't many cell towers nearby, then the accuracy can drop significantly to the point where it could be several city blocks or something like that in terms of knowing where you are.
Okay, so Sean, I would like to say thank you so much for today's great and informative presentation. I am going to launch today's evaluation. If you could take a few moments to complete the evaluation, as the feedback provided is not only important to Sean, but to the entire Cutter Transportation webcast series. Okay, thank you everybody, and we'll